here we're going to have a look at probably one of the trickier year 12 concepts, and that's the idea of Hess cycles. Now, the reason we teach Hess cycles and the way I'm going to go through them is because if you do it the way you do at GCSE, which is products minus reactants, it gets you into bad habits for when you have to do lattice enthalpy and when you have to do enthalpy change combustion, which is slightly different. So we're going to try and do a different method called a Hess cycle. And the idea of a Hess cycle is that it doesn't matter what way you get from the reactants to the products, the energy is always going to be the same. So this pathway will have the same energy change as this pathway, will have the same energy change as this pathway, right? And in order to, and this one here, this can't be measured directly. So what you have to do is you have to find the enthalpy change of formation. And the definition of that is the energy change that occurs when you make a product from its constituent elements in their standard states. So what I mean by that is if I've got, let's say, Fe2O3, so iron oxide, their constituent elements would be iron and oxygen. But it wouldn't just be iron and oxygen, it would be iron, solid, so FeS, and oxygen, O2G, so O2 as a gas. So it's the way those elements are found in standard conditions by themselves. So that's the enthalpy change of formation. Now you do it as 1 mole of the product. So to make 1 mole of iron oxide requires 2 moles of iron and 1.5 moles of oxygen. But the moles of the reactants don't matter, it's the moles of the product. Okay, and formation arrows always go up. And so this is why we get the products minus reactants, because to get here you have to go through this method. And if I go against the arrow, then I do that as a minus. So this, to go from there to there, I have to go against the arrow, and therefore that's minus. So that would be minus my value of HF2, so the enthalpy change of formation for the reactants, and this going with the arrows, that would be plus HF1. So therefore my formula for delta H equals HF1 minus HF2, or my products minus my reactants. So let's have a look at how this works. In this case, I've got this reaction. So I've got tin oxide and some carbon monoxide producing tin and carbon dioxide, and I can't measure that directly. So this is the value I'm trying to find. So what I need to do, and I've got some values for enthalpy change of formation down here. What I need to do first is break it into constituent elements. So I've got tin, which is Sn, I've got carbon, and I've got oxygen. Now, in its standard state, tin is a metal, so it's solid. Carbon is solid, and oxygen is O2 as a gas. And we should really balance that. So we've got the right number of tin. Oxygen is 1, you've got 2, 4. So I've got 4 oxygens, so I would have 2 there, and I've got 2 carbons. All right. Now, because this is a change of formation, my arrows are going to go up, and I've got to figure out what the value of this arrow is and this arrow is. So the value of the arrow on the right, so my products, would be 2 times the enthalpy change of formation for CO2, which is minus 788, I believe. So it's minus 788 for 2 moles of that. Let me double check that. So 2 times 394. Good, right. Now, I'm not going to do it for the tin, because the tin is a solid state there and a solid state there. So it hasn't actually changed from this to this. Now I've got to figure out the energy change for this. So that's going to be my tin oxide, which is here. So that's minus 581. And then I've got 2 moles of carbon monoxide, which is minus 222. That's 2 times 111. Now, if I put those into the calculator, 581 plus 222, that's going to give me minus, as a value, 803 kilojoules per mole. And because I'm going against this arrow, that's going to turn into a plus. And with this arrow, that stays as a negative. So my value, my calculation would be minus 788 plus 803, which therefore equals 15 kilojoules per mole. And kilojoules per mole. I just haven't got the room to put per mole. So that would be how you'd find the value for delta H. Okay. Slightly different with combustion, because with combustion, the arrows point down. So on the bottom, you're always going to have carbon dioxide and water. And if they give you the values for the enthalpy change of combustion, like this, you would do the same thing. You'd put them on the arrows. But because you go with the arrow down and then against the arrow to go up to the products, it changes around. So it becomes reactants minus the products because you're going against the arrow. And then there's your calculation.